Okay, now we're going to look at pneumatic switches, which are called valves. This type of valve is called a spool valve. It's got a solenoid at one end. Inside the solenoid is a poppet or a jumper. Solenoid's got a solenoid coil, and we also have a shuttle, and it has ports. Ports are holes where air can go in and come out. Now, I've made a note to tell you the naming. The way we name these things is we name them by the number of ports and the positions. So this solenoid valve here, this has got 5 ports. So it's got 1 there. So 1, 2, 3, 4, and 5. It's got 5 ports, and it can be in 2 positions. So this is called a 5-2 valve. Okay, now the way this works, we've got a solenoid coil here. We energize that solenoid coil, and when we energize that solenoid coil, it turns into a magnet. When it turns into a magnet, it should pull the poppet or the jumper, and the jumper should jump. So this is what these things look like. They look like this. Here's a 5-2. This is another 5-2, and this one looks like a it looks like a 2-2 actually. So these are what these things look like on the outside. Here is the solenoid assembly with the coil there. And here's the solenoid. Okay. Here's how it works. We energize the coil. Now I've got mains air here. Mains air going through there. What this is doing is it's working a piston. I might draw that in a better colour. It's working a piston. So I've got a piston here. Okay. And this is connected to there, and that's connected to there. So I've got mains coming in there. And as the piston moves in this direction, exhaust air is allowed to come out. It's very important when we're working pistons that we let the exhaust out the other side. Otherwise, it doesn't move. So what I've done here is I've energized the coil. And when I energize the coil, the jumper jumps. What would happen if the jumper got stuck and failed to jump? Okay, now the way this thing works is the coil gets energized. You put electricity into it. What's supposed to happen is that the jumper's supposed to jump. Then we have a nice big chunk of iron in the middle of the coil. The coil magnetizes this chunk of iron. The chunk of iron then it then has a magnetic field, and back EMF is put back into the coil. So we get back EMF put back into the coil. That back EMF limits the current flow through the coil. If the jumper doesn't jump, we don't get any limiting of the current through the coil. And if we don't get limiting of the current through the coil burns out. So a very common fault with this is that the coil burns out. As an electrician, you'd have come along and replaced that coil. Then you would have noticed that the jumper still didn't jump. So typically what you do is you hit it with a spanner, and then there's a nice satisfying click sound, and it all seems to be working, so you walk away. Now that's only a temporary fix. The problem is that for some reason the jumper is getting stuck. So just replacing the coil and hitting it with a spanner is just going to keep it working for a couple more days. What you should do is replace the entire solenoid assembly. The whole of this solenoid assembly should be replaced. Okay, now I'm just going to delete that, and that's a shame I don't have enough. I'm just going to, yep. So this is the, I'm just going to delete all the marks on the other. This is what the spool valve looks de-energized. When I energize the spool valve, the poppet jumps to this position here. So the poppet or the jumper jumps to here. When it jumps to there, it allows mains air to appear on this side of the spool. Mains air on that side of the spool pushes the spool valve, pushes the spool over. When the spool is pushed over, the air is directed from the center there to the left-hand port. Going back to the de-energized state, you'll see that the air goes in there and comes out of the right-hand port. So in its de-energized state, the air is coming out of the right-hand port and return air is able to come out there. This port here is completely blocked off. In the energized state, this port here is blocked off, mains air is on the left-hand port, and the return air is allowed to come this way. So when we energize this, the spool shifts over and the air switches. It's an air switch. Are we all happy to move on with that, or do you need more explanation of how it works? Right then, now I'm going to tell you how we draw the circuits. I'm assuming you all know how to draw electrical circuits, so I'm going to describe everything by comparing it to electrical circuits. With electrical circuits, we draw everything in the relaxed position. This is an electrical switch. How would you describe this electrical switch? Yep, what I'm looking for is it's a double pole, and it's a double throw. This is a pneumatic switch, and we describe it similarly. We describe the number of ports. So this is a 4-port, 2 position. So it's a 4-2. With pneumatics, we draw every possible position. So, as well as drawing it in the relaxed position, we draw it also in the energized position. The way we differentiate is we draw, the first thing you do is you draw a square. It's called the block. So you draw a square. And you draw a square for each possible position. And then within that square, firstly we draw the relaxed position. In this case, so there's my ports coming in, 4 ports. In this case, in the relaxed position, everything is blocked off, nothing's connected. And then I'll draw the other position. And in the other position, I'm connected across. So the first difference between fluid power is that we draw every possible position of the switch. If it was a 3-position switch, say we had another couple of poles there, this made like that, then that is a 3-position switch. If it was a 3-position, we would have to draw another box. One box for every possible position. And that might be showing it crossing over like this. So with fluid power, we draw a box for every possible position of the switch. You don't just draw the switch in the one position in its relaxed position, you draw every possible alternative. You know which is the de-energized state because when you do the circuit, you always do the wiring to the de-energized state. What would make it clearer is if I put a spring underneath there. With that spring, the spring would tend to push that upwards. So we know that the bottom is the de-energized state. But when you're looking at the circuit, the wiring is always put into the de-energized box. So you know which is the de-energized state. Right, so, second problem with fluid power. With electricity, it's all right to draw the switches the way I've drawn them, because with the switch open, the stuff doesn't leak out the ends. With fluid power, it does leak out the ends. With fluid power, you have to actively shut the ends off. You can't just open them up. So with fluid power, we put these little stoppers in, these little things, the little T's. That symbol tells you we are actively stopping the end off, because if you don't, it will leak out and make a noise. Okay, so here is a shuttle valve in its de-energized state, and this is the symbol for a shuttle valve. Now, those of you that have the books, there's a glossary of these in your book somewhere. I haven't got the page number written down. This is the symbol for a pilot. It's called a pilot actuated because it has pilot air, which is shoving that shuttle across. And this is the symbol for a solenoid. These things here, they're the symbols for exhausters. How do you spell that? They're the symbols for exhausters. So we have mains air arriving there. Mains air. There are two symbols for mains air supply. One is a circle with a thing coming out. Another one is a triangle with a thing coming out. That's mains air. Mains supply. So that's the de-energized state of the solenoid. The energized state of the solenoid would look like this. And you have to imagine that we've switched over to the other box, and so the air is now coming up here and going out on that side, and it's returning this way. Whereas the previous one, the air is going up here and going up that side, and it's returning this way. So, de-energized, energized. If I just switch backwards and forwards, you can see how the shuttle is moving. The spring here, this is a symbol for a spring. The spring is being compressed, and this is a symbol for a spring. The spring is being compressed, and the air is being switched from left to right. Okay, so that's a pneumatic switch. Now, there's a bunch of pneumatic exercises in your books. Some of you may have access to a program which is called Fluid Sim, which allows you to draw these things using a library and simulate them. Some of you may have access to pneumatics where you can build these circuits. I would like you to do some of those exercises. If nothing else, just do them just by drawing out the circuits. Okay. Energize. Right. So reading pneumatic symbols, the block. Every position has a block. So every possible position of the switch has a block. There are specialist symbols like a solenoid. Symbols which means exhausts. Symbol which means supply. The T's, that shows where we're blocking stuff off, and that's a spring. The arrows indicate where the fluid, well, the air flows. So this valve here, this valve has got 5 ports and 2 possible positions. So it's called a 5-2 valve.